All right, welcome to lab number, as you can see up here on the screen, lab number 6. It's called RC circuits. Now this is a nice experiment because you've basically seen the data that you're going to get from this experiment from the previous experiment, lab number, lab number 3 on capacitive circuits. So now we're actually going to study how the current flows in a circuit that has a resistor in it and a capacitor. So in the drawing right here, you can see I've got this arrangement where there's a switch up here, and this switch is called a double throw because it's got 2 points it can go to, and this is a single pull, double throw. Okay, and so there's one pole right here and then 2 poles here. So I can switch from either this line here, which includes a battery in the circuit, and then the other one, when I do that, the battery's eliminated, and I use that to discharge the capacitor. So once the capacitor gets fully charged by a battery, then I can discharge it, and we can look at that behavior as well. Because when we study RC circuits, you need to be able to understand the mathematics that go into describing how a capacitor charges and discharges when you hook it up to a power supply, a DC power supply. Notice this side's positive, this side's negative. So this capacitor plate will become positive, and this side over here will become negative. All right. So lab number 6. Now the math for it is based on Kirchhoff's loop rule, so we're going to do charging first. That means we're going to have a battery in the circuit, so this is when you throw it and include the battery. So current comes out and loads up the capacitor with charge. Now as you know, as we described earlier, when you put more and more of the same type of charge on a plate, it gets harder and harder to move more charge onto that plate. So in the very beginning, when there's no charge, it's very easy for current to flow out. In fact, the capacitor acts like a wire for 1 instant when you throw the switch. So that means the entire current is flowing at t equals 0 as though there were just one resistor in the circuit, and you can use V equals IR to determine what that maximum current is. All right? And so anyway, this is the setup right here. And Kirchhoff's loop rule says if you go around a loop, then all the voltages have to add up to 0. Now, this is a voltage rise, that's your power source, then voltage gets dropped here, and then voltage gets stored over here. Okay, so that's like a drop, but you can actually get this energy back. You can't get that energy back. All right, so up in the top here I've written Kirchhoff's loop rule for the circuit. I put the battery voltage, which is constant, on the left side of the equation, and on the right side is V equals IR, and then this voltage here is Q over C. That's a definition of capacitance, all right? So V equals IR and Q over C. Now the definition for current is the change in charge over time. So this value I is the same as dq dt. And from your differential equations course, you can see now that we have a differential equation that will require us to separate the variables. So one variable, the independent variable, is time, and the other variable is charge, the charge that's going to appear on the capacitor. All right. Now the other numbers are all constants. So these would be your controls in your experiment. So you have R, C, and V. All right. Now let's separate the variables. That's something you're taught in your Diff-EQ class. So we're just going to jump down to this equation right here. And basically what I did was I multiplied through by C, and then V times C is Q, the total charge. So once a plate gets totally charged up, then you can see over here on this equation, Q is equal to voltage times capacitance. So I multiplied both sides through by C, and then R and C are together here, RC. That's a very important number. It's called the time constant of the circuit. And then C is over here with voltage, and that becomes big Q. Right now I left it as just V times C, but then it'll become big Q down here. All right, I also took a minus sign out, so when I separated them, I put a minus sign right here. Because as the circuit runs, the current's going to decrease. All right, and it's going to decrease exponentially, as you've seen. And that exponential decrease has a negative in the power. So I know what the result's going to look like, and so I can anticipate when I go to solve it ahead by putting the minus sign over on this side. All right. Anyway, if you look over on the right side of the equation, we want to look at the circuit. It starts from no charge on the capacitor to some point in time where there's Q, little q amount of charge. Now remember, big Q is the total charge. Little q is whatever charge the capacitor is charged up to as time goes by. And so when t equals infinity, then the total charge will appear on the plates. Now, infinity is a weird number because for the circuits we look at, it's only about 10 seconds. It's not like the end of time. All right, so anyway, you can see this is a log right here. It's not a nice clean log, but when you integrate that thing, you get a log. And over on the right, on the left side over here, this is very simple. These are controls right here, so you just get t. And then once you get the log, then you can do the inverse log to both sides and turn it into an exponential equation. So the charge on the capacitor at any time t is equal to the total charge and then 1 minus e to the minus t over, and this symbol right here, tau, is called the time constant, and it's equal to r times c. So let's talk about that for one quick second. If I made this resistor larger and larger and larger, it would be harder and harder and harder for the current to flow to charge up the plates. So you see, so this affects the timing of the circuit. In the same way, if I made the capacitor bigger and bigger and bigger, for a given voltage, you can put a lot more charge on the plates. So once it's at 1 volt, if it was a small capacitor, there would be very little charge on the plates. But for the same single volt, 1 volt, you'd have much more charge. And remember, the resistor is slowing things down, so it'd take longer for that charge to build up. So the combination of those two numbers turns out to be a time unit, and it's a measure of when the capacitor has charged up about 67% of its value. So after one time constant, and we'll show you in 1 second, it's charged up to 67%. Here, I'll show you that the time, so it comes out to be time. So if I take R and I multiply by C and then plug in what they are, so you can see R over here is equal to voltage over current. And remember, current is in coulombs per second. So that's current right there. And then I'm going to multiply by C, and you see C over here is coulombs over volts. Okay? And you can see the C goes out, the V goes out, and then you're left with seconds. And so that's a time constant right there. And so that affects how long it takes for the capacitor to charge up. And you're going to study that in the experiment. So let's go to the next slide. Now once you get the equation we just got, so as time goes by, e to the minus t over tau will go to 0. Because anytime you have a negative power on exponential, it's a number less than 1. And in fact, it's an exponential, so if I put in like minus 5 up here, that is an extremely small number, and that would be 5 time constants. So basically, when t becomes 5 times the denominator, that's when t is equal to infinity. And I'll show you that in again. And so this number right here goes to 0 in time, and then you're left with just q, which is the charge on the plates after an infinite amount of time. Now if I take the derivative of this equation, I get current. And so the current, you see this is a control, so that goes to 0. When you take the derivative of a number, you get 0. And so you get q, and then you're going to get tau that's going to multiply by q, and you're going to get current out of this whole thing. And remember, q, if you go back over here, q is related to c and v, all right? And tau also has resistance in there. And so when you work all that out, you get the maximum current right there. All right. In fact, I did it for you right here. So anyway, you get those combinations. V over R is the maximum current. Remember, that occurs at t equals 0. When t is equal to 0, that's when the current is a maximum. All right. Now, how do I get the voltage across the resistor? So I take the current, all I do is multiply by R, which is a control. And so there's the equation right there. It looks just like that equation, except now it's got VR here instead of I naught. Because I naught times R is the V across the resistor, and that's the voltage on the power supply. At t equals 0, all the voltage at t equals 0 is across the resistor. All right. And now how about the voltage across the capacitor? Well, voltage for a capacitor is Q over C, and that's a little bit more complicated. So I've got Q over C, which is voltage, capacitor, and then 1 minus e to the minus t over tau. So eventually, all the voltage is across the capacitor, and that's when it's fully charged. Okay, so when t is equal to infinity, which is about 5 time constants, the capacitor is completely charged. All right, so here's what the graphs look like. Now I'm going to get over here so we can look at the graphs. So I'm looking up here at the top, and you can see this is the charging of the capacitor, and after 1 time constant, so you turn it on, and time goes by, and the charge is going out of the capacitor plate, and when you get to right here, see 63%, fully charged. When you get to 5. So you see out there, that's the magic number, 5 tau, 5 times the time constant, and the capacitor is basically fully charged. All right, now the current in the circuit is going down, down, down because it's getting harder and harder and harder to put charge on the plates. So it falls exponentially and essentially goes to 0 after 5 time constants. And you can see after 1 time constant, it has already lost 63% of the current that it had at t equals 0, the maximum amount. All right. Now the voltage across the capacitor is going to be just like this curve right here, because all you're doing now is, remember, charge and divided by capacitance is voltage, and capacitance is a control, so it's the exact same looking graph. All right. And the voltage across the resistor goes down just like the current. V equals IR, and then over here, capacitance equals Q over V, so these are the same type of graphs. All right, now let's discharge this thing. We're not going to spend a lot of time on this because it's the exact same math, but simpler. All right, so anyway, this time we throw the switch and there's no battery, and all the current, all the charge on this negative plate. So remember, this plate was negative, this plate was positive, and really electrons flow from negative to positive, and so this time the current will flow in the opposite direction. Current will flow in the opposite direction. All right. It'd be just like the positive we're unloading and going this way. It's the same as the negative unloading and going that way. And we know that current really is the flow of electrons. All right, so Kirchhoff's rule says, oh, there's no battery, and so we just have the voltage across the resistor plus the voltage across the capacitor, and we get that same relationship. And we go ahead and separate the variables, and notice there's no voltage, so this is really simple. That's a natural log, and it'll give you the log of big Q, like minus the log of little, actually log of little q minus the log of big Q. You can exponentiate both sides, and there's your charge, leaving the capacitor as time goes by. All right, so anyway, now we can go ahead and you take the derivative, you get the current. Notice the minus sign. Minus sign means current flowing in the opposite direction. All right, and the voltage across the resistor is I times R, so it's the exact same relationship, except now it's voltage. I should have a minus sign here because it's losing voltage. All right, and then over here, VC is Q over C, and remember Q's up here on top, and Q over C, e to the minus t over tau, and that's the equation right there. And so here's what the curves look like. So I'm going to get over on the other side so I can look at them with you. You can see it's unloading, exponential decay. Remember before it was loading, so it looked like this before, but now it's unloading all that charge. And again, after 1 tau, it's lost 63% of its charge. It's lost 63% of its voltage. The current, notice it's got a negative number here. It's a max in the beginning, because remember, there's no battery. The only thing that's keeping the current from flowing super fast is a resistor, and so that decreases 0 along that exponential decrease going backwards. This should have a minus sign up here. Sorry about that. And up here, the voltage across the resistor is this value here, so it's got all this voltage, and it's decreasing, decreasing, decreasing. It turns out that actually with the voltage, it doesn't matter if current goes in one side of resistor or the other side. All it does is take that current and turn it into heat and light, which is a really physical, positive physical quantity. Okay, so this is actually accurate right there. All right, and then just one last thing before we turn this off. If you've ever worked with a camera and you turn the flash on to the camera, you push the button, you want the flash, you'll hear the camera, some of these big cameras have a big flash. They will go and make a sound as it's charging up a capacitor. All right? And so basically, if you go back to our first slide, you see the battery's in there, it's charging up a capacitor, and it's doing it slowly because there's a resistor in the pathway. In fact, the resistor's like right over here, all right? Then, when you want to take the picture, you push the little button, and it moves it from this position over here to this position. Now remember, the only resistance now is the flash, the little filament inside the light bulb. It's got a very, very low resistance, and that current unloads, the charge unloads, produces like max current, boom, right away, and produces that flash and allows you to take pictures when things are dark. Okay, so that's it, and now we're going to do the experimental portion, but we always save that for the next video. Over and out.